All right, good. So you're most welcome. Please begin by subscribing. I told you that's the token or the thanks or the appreciation you can give, or more like a thanksgiving. Okay, so we are looking at lesson 5, the last topic in linear motion, the first topic of mechanics we have so far begun with. So it is lesson 5, velocity time graphs, and this is the last bit. Now, UNEB this year, UNEB 2024, they set a number, or rather, UNEB last year, 2023, they set a number on a distance time graph. You will look out for it, or we shall also do it here. Okay. Now we are saying, when do we use the distance time graph? Now, there is something you must know is, whenever you see the word constant acceleration, whenever you see the word constant acceleration, whenever you see the word uniform, the word constant is the same as uniform. Whenever you see the word uniform acceleration, constant acceleration, then you just know we are going to go by calculations to find the answer. But if again we see a constant acceleration, then after some time it changes. Like say for example, a body was moving at 2 meters per second squared. Then after 10 seconds, it again moved at 6 meters per second squared. Once the accelerations are changing, when the acceleration is changing, it means that we must use a velocity time graph to get that answer. Okay, we are saying when motion takes place and acceleration changes after a given time interval, the solution to such problems can be obtained using a velocity time graph. So when you read a word problem, one from linear motion, and you see that the same body, the acceleration is changing, then you just know that we have to use a velocity time graph. Though we are lucky that when the examiners are setting, they tend to always bring it direct. Use a velocity time graph like that. Okay. Now, a note, what must you know? What are the terminologies you will see in there? The terminologies you see in any question requiring a distance time graph will be uniform acceleration, uniform deceleration, then uniform velocity. Those are the three words you should expect, and please pay attention to them. To begin with, we have uniform acceleration. What must you know? Remember we said acceleration is the rate of change of velocity. The rate of change of velocity, or back then some people used to say, is the change of velocity with the time. Okay, so when velocity is changing and time is changing, then we have acceleration at that very moment. Remember, velocity is the same as speed. The more you run at high speed while time is going is what we call an acceleration. Okay, so now uniform acceleration, the line must be in this format. Please, somewhere here you must cram them. Uniform acceleration should be like this, moving upwards. Then uniform deceleration, it must be coming from up downwards. It is more like this, but an opposite. Then finally, a uniform velocity. A uniform velocity must be like this, a straight horizontal line. Whenever I see this word, uniform acceleration, the shape should be this. The uniform deceleration, the shape should be this. Uniform velocity, the shape should be that. Okay. All right. Now, what if when we get all these guys and we combine them together? What do we really get? So combine the stages. We have, of course, by the way, labeling the axes is highly called before. Labeling the axes is highly called before. All right, so we have the combined stages. You see that this one is the first one, this one is this, and the last one is here. So that here we have uniform acceleration, uniform velocity, uniform deceleration, like that. Now, when you get to combine the stages of those motions, then it means that you can come also and divide them like that. Split them down into stages. And when you split them into stages, what do you see? Which shape is this from here up to here? Which shape is this from here up to here? Which shape is this from here up to there? So realize that it is shape. This one is a triangle, rectangle, triangle. Now, before you can call them, we shall call this X, we shall call this Y, and then we shall call that Z. Now, a question will come after you have drawn that distance time graph, rather a velocity time graph, then they will ask you, find the total distance or displacement covered by the particle. What do? We say from the graph, the total displacement or distance is calculated from displacement is equal to total area under the graph. Meaning, this word is graph, please. Graph, total area under the graph. And now that means that, we have to get the area of X, the area of Y, plus the area of Z. With that, shall have the total displacement. And now this means that total displacement S will be equal to area X, allow me just call it that, area X, plus area Y, plus area Z. Displacement is equal to area X plus area Y plus area Z. And that's what we all need. That's very important. We now go straight away to the real examples and we see the way forward. All right, let us proceed. We have an example here. They're saying a car starts from rest. A car starts from rest. You take note of that. A car starts from rest. So solution. A car starts from rest, accelerating at 1 meter per second squared. So now whenever you're summarizing, this one will be our stage 1. This will be our stage 1. Okay. A car starts from rest, okay, meaning that its initial velocity is 0 meters per second. Accelerating at its A is 1 meter per second squared. For 10 seconds, the time for the first stage is 10 seconds. For 10 seconds, full stop. A car accelerates that for 10. A car accelerates at that for 10 seconds. Now, when it's accelerating for that for 10 seconds, meaning that it's accelerating at 1. At 1 for 10 seconds. As the 10 seconds are going, the car is accelerating at 1. That means that this acceleration is uniform for the 10 seconds. And then what do? They want in part A, draw a velocity time graph. And then what we're going to do here is simple. Just come and draw this. You can put the title, velocity time graph, no problem. Put your title, a velocity time graph. So you're having that. Please here they must intercross like that. So here we have time in seconds. Then here the velocity, we have it in meters per second, like that. Now I'm going to draw. Remember, we are saying that this is stage 1. When you begin reading, that is always stage 1 now. The initial velocity is 0. Okay. Now the acceleration is 10 for 10. The acceleration is 1 for 10 seconds, meaning that it was uniform. What you should know whenever dealing with the questions of linear motion, they must always have uniform acceleration regardless. So this was indirectly 1 meter per second squared for 10 seconds, meaning that this is a uniform acceleration. And then you remember what we said. Once you have this uniform acceleration, uniform velocity, uniform deceleration, please, you can rewind back the video and see those terminologies. Now, you come and say, this is the time in seconds. Now, I will say, the time in seconds, maybe here I will say, from here up to here, in simple terms, I will call it, okay, this is the time. Now, I will say, its time is starting from 0, even the velocity is starting from 0. Upwards, time is starting from 0. So realize that from here up to 10, from here up to 10, maybe I can even add. So from here up to 10 there, from here up to 10, the body was accelerating uniformly. That means that this body, can put this, you start from where? This is the first time we have is going up to that level. I can end anywhere you want. It has no right place it should end. Okay. I'll leave it as that. Please, it has no specific area where it should end. Never. Now we know that this one here, this is where we are now. Where it has reached like this, that means that it will have reached the final velocity v. So this side I'll put the final velocity v, like that. Please, why am I drawing this? Because uniform acceleration is in this order. You can rewind back the video. Why uniform acceleration? Because the acceleration was 1 for 10 seconds. It was not changing for all those 10 seconds. It means that is the uniform acceleration. So for this area, the acceleration is equal to 1 meter per second squared. That is stage 1 done. Okay. Now the time helps me a lot to know how I'll cover up the stage. It was for 10 seconds, so I've adjusted 10 seconds up that level. Like that. Proceed. They are saying it continues at a steady speed, meaning that a steady speed, steady means a uniform speed. It has not changed. If it was at 20, if it came like this and ended at 20, it still continued with the 20 at a steady speed. It still continued with the 20. Or if the final speed was v, it still continued with the v. For how long? Let's see. It continues at a steady speed for 20 seconds. For 20 seconds. So you know that this is your 10. Now the 20 will be how? Will be here and somewhere here. Yep. Like there. Now it continued with a steady speed. Now the 20 will end somewhere here. The 20 will end somewhere here. The 20 seconds will end somewhere here. Now it is continuing with a steady speed. Like that. Now that's the steady speed. Now if it is 20 from this, then here we shall be at 30 what? Seconds. The time helps you a lot on how to bring out that. All right, now 20 seconds, and it decelerates to rest in 5 seconds, and decelerates to rest in 5 seconds. We said decelerating is this one when it is coming downwards. So in 5 seconds, it means that if this one was 10, halfway it is the 5. You always try to estimate is 5, halfway it is 5. So therefore, the 5 will be somewhere here. In simple terms, my 5 will be there. So now it decelerates to rest in 5 seconds. Now 5 seconds from here, this will now become a 35, like that. And now what we have is our velocity time graph, or the drawn. 9 marks for that. 9 marks for that. Okay, good. Let's now proceed. We are done drawing the velocity time graph. Please, some people think that you must have this be known. No way. All you must know is how to get the time and go up. Are you obeying the uniform acceleration? Are you obeying the uniform velocity or steady speed? Uniform, steady, constant, they are the same. So steady speed, are you obeying the deceleration? Those are the terminologies you must pay attention to. Okay, then and find the distance covered, and find the distance covered. So we shall now say distance covered. Distance covered, we shall now say distance equals to, we know that total distance covered is equal to area under the graph. So area under the graph. So we have area of A, we have area of B, I'll call them that, then area of C. Please, any naming you use, no problem. Someone can call it 1, 2, 3. Okay, is equal to area of A plus area of B plus area of C. Please remember to put the title and also to label the axes. Time in seconds, and then the velocity meters per seconds. Okay, good. Now, what you must see is, here we have a triangle, and you all know that the area of a triangle is a half base times height. That is it. Now let's see. Area of A. Now what is its base? The base is from here up to here. Now you get 10 minus this. In fact, what you will do, you will allow me to write it there now. 10 minus this, you will allow me to write a demo. Just a 10 there to mean that the base is 10. Then, what you must know is from here up to this side. Now here, from here up to here is that final velocity. Do we have that final velocity really? No, we don't have final velocity. And please, stage 1 helps you to get that final velocity. So if you have this, stage 1 helps you to get that final velocity. From that final velocity is always good from V is equal to U plus AT. Like that. So V, the final velocity, which shall put there, is equal to 0 plus 1 times 10. So V is equal to, that will give you 10 meters per second. Please, the first stage gives you the V. So our V is 10 in simple terms. Allow me to put it as 10 there like that. Okay, good. Now, to do that, the height from here up to there, is 10. So therefore, this will be equals to a half times the base is 10 times the height is also 10. Oh, like a way. Plus area of B. B is a rectangle. Now you subtract this minus this. Please here we subtract a 10 minus 0 to get us this. A 10 minus 0 to give us a 10. Here also we maintain the 10. Now from here, this minus this, 30 minus 10, it will give us a silent 20. Please, I'm putting them there for you to see. Then we have a 20, we have a 10. So how do we get this? Area of a rectangle is equal to length times width. So length is, all right, 20 times 10, which is the width, plus. Now area of C will be a half times, what is the base from here up to here? 35 minus 30 is 5, times the height is the same, from here up to here is 10, like that. Then you calculate and give us that answer. So this and this will cancel to give us 5. So in the first point we have a 50 plus, this time this will give us a 200 plus, okay, this and that gives us 25. A 25. So your total distance here will be a 275 meters. The total distance covered in there. It is just something simple. Okay, good. Lastly, that's the part B. Part B, they are saying, okay, calculate the average velocity. Now, the average speed. We all remember from this. From this, You all know what to call the DST. DST. Now they're saying average speed, but we know that speed is equal to distance over time. So average speed, we shall say, average speed is equal to total distance, because speed is equal to distance over time. So total distance over total time. So total distance over total time. And that will be total distance is what? Total distance is 275. Then total time, the time they took from here up the end is 35 seconds. 35 seconds. Then here your average velocity will be, you divide there and give us that answer. So your average velocity will be a 7.8571. A 7.8571 meters per second. As simple as that. That's how simple the velocity time graphs are. All right, so let's look at another version and we call it off. They're saying a motorist moving at, I told that's always stage 1. That is always stage 1. So stage 1, a motorist moving at 5 meters per second. So our U is 5 meters per second. Okay. Accelerates uniformly at 1 meters per second squared. So A is 1 meter per second squared. Accelerates uniformly at 1 meter per second squared. For 10 seconds, T is 10 seconds. That's stage number 1. Let's go and draw that. Now, unlike the other first example we did, you can rewind the video to see. This one is a bit unique. This one is a bit unique from the other one. Okay, so this is now time in seconds. Okay, good. Now, we have this. This is the velocity in meters per second. Now, they are saying a car accelerates uniformly, rather, starts from, now, the other one we had started from rest, that was 0. That's why our graph started like this. Starting from 0, it must begin from here and it goes like that. But cases whereby it's not starting from 0, please, this is how we go. Now, started from 5, the initial velocity, we always pay attention to the initial velocity. The other first question was, initial velocity was 0. Starting from rest, here it is 5. So if it is 5, you come and begin from here. Somewhere up here, then you say, now this is my 5. There. That's the way my velocity is going to begin from. And since now they said accelerates uniformly. And now for uniform acceleration, we know it is in this order, like that. But for how many seconds? For 10 seconds. So my 10 seconds, maybe they will end here. So this is now the 10. This is 0, this is 0. That's the 10. 10 seconds. So that my motion must move. My motion must move up that level. Okay, use the ruler always. So my motion must move up to that level. Are you seeing where it is starting from? It is starting from somewhere here. Because it is starting from at 5. They can say at 20. But if they say from rest, the beginning is from here. Some people have the problem work, and the time they have this question, they start from here. And please, you can go and check for UNEB 2023. I think that was something like number 9 or 10. You go and cross-check. It required something of this kind. You're not starting from a rest. Okay, good. Now let's proceed. We are done with that. So my emphasis was at this point. It is not starting from 0. They are saying for 10 seconds, yes. It continues at a steady speed for 20 seconds. So mean that now where it has reached at this level, it is now at its final velocity. Now, and it continues with that velocity for 20 seconds. So mean that from there up to around here, that is now our 30, it continues like that up to 30, because 20 plus 10 gives us a 30, like that. Proceeding, then the saying, and decelerates to rest in 5 seconds, and decelerates to rest in 5 seconds. So the 5 seconds it will be somewhere here. That's now at 35. Comes and rests to rest at that point, like that, as simple as that. Good. Now, what next? We are done drawing our graph. What next? They are saying find the total distance traveled. No problem. Distance is equal to, now you can label. Now I don't know what you prefer. But okay. This one here, I'm seeing this one is a trapezium, a rectangle, and a triangle, but you can decide to split it like this. So this one becomes your A, this one becomes your B, this one becomes your C, this one becomes your D, like that. Since some people may be not okay with the trapezium, so we shall now say displacement S is equal to total area under the graph. So that will be area A plus area B plus, okay, area C plus area, right, D. Then let's start. Area A, this one is a rectangle. We shall now say it is equal to, by the way, we need to get our final velocity. This B. And now this one will be, I thought that final velocity is got from the first stage, and that's from V is equal to U plus AT. V is equal to U plus AT. So therefore, what is our V? The final velocity we are looking for, our U is 5 plus the A, which is 1, times the time taken in that first stage is 10. So when you apply, you see that you will get 15. The SI unit for velocity is meters per seconds. Then this one here is our V. So you look at this V as our 15 there. Without it, you can't get the area. So here we shall now say area A is this, from here up to this. Now you know that from here up to here, this one is the same as 5. From here up to here is 5. So therefore, we are now going to say, what's our length? From here up to here, you say 10 minus 0. Here we have a 10. Then here you say a 5 minus 0. Here we have a 5. So let's get the area there. The area will be, it is a rectangle, length times width. So the length is 10 times the width, which is 5. Plus, now area B is a triangle. A triangle whereby you know that a triangle is a half times the base will be, now from here up to here, it is 10. Like that, times the height from here up to here. So now you must put in consideration that from here up to this, 5 to 15, you subtract 15 minus 5, and that will be a 10. So that's also 10 plus area of C. C is here and is a rectangle. From here up to, you subtract 30 minus 10, and that will be a 20. Then also from here upwards, it's a 15. So therefore, because here, this from here up to there, it is a 15. So therefore, we shall say a 20, which is the length, times the width, which is 15, plus. Now area of D, this triangle. Maybe let me put it right. Okay. Like that. So we now have a triangle is a half base height. So the base is 35 minus 5 minus 30. So we shall say a half times this minus this will be now 5 times the height from up here is 15. Then from there you get your calculator, compute, and get that answer. So this one will now be equal sign. We have a 50 plus. Here you cancel. You shall again have a 50 plus. All right, 20 times 15. 20 times 15, that will give us a 300 plus a half times, here you can use a calculator. So that will be a half times 5 times 15. A half times 5 times 15. Shall now have, all right, so let's complete up that. So here when you multiply, you get 37.5. So here now we shall add, that will be 400. So the final answer will just be 437.5 meters. And that is our displacement total. Please, this one is here is a very good clarification. Some people have problem work that you must start from 0. No, for this one it was a unique case. And we have that. Please don't forget to subscribe.